Hello guys, welcome to the fourth session of Cassandra Learning, the series for software development for non-technical people. First of all, I wish to apologize to you all for not posting videos for the past 2 days. Extremely sorry. I couldn't do it because I'm down with a bit of a viral fever. Now I had recovered and I am okay to do the session. Thank you. So thank you for being patient with me and following me. So this session is going to be an interesting session. This is about the evolution of how the software development process came about, and this is going to be very interesting story for you because this very similarly resembles to our human evolution. It's very similar to our human evolution, how human evolved and all that stuff. So, the compare and contrast between the human evolution and the software process evolution is going to be very interesting for you. So please follow, guys. Let's get into the session. Before that, the recap of the last session where we saw it is for a program to function, we not only need instructions but also data. We saw an example of adding two numbers, and the two numbers we input are the data and the plus symbol is an instruction, all that we saw. And all these things needs to be coded into machine language for the machine to understand and process it. So for that, for the instructions, we used something called as assembly language and assembler, and then we convert it into machine language, the ones and zeros. Whereas for data, we use something called as an ASCII code. ASCII stands for American Standard Code for Information Interchange, and it is a standard way of converting characters into binary, the ones and zeros. So, we also saw about Unicode, which is a modern coding system, which is of multi-byte in nature, whereas ASCII, every ASCII character is of size 1 byte, which is 8 bits, whereas Unicode will be of 2 bytes or more than that even, and it can accommodate a larger number of characters henceforth, and I think it can accommodate up to 65,536 characters, which is more than enough for including all the characters and special characters of world's popular languages. So that is what we saw in the previous session. Now we are going to see the evolution of software. So before getting into the evolution, we need to understand what is a programming logic. So every program, we say we follow some logic to accomplish a particular task, right? In every program, basically every program is written to accomplish a specific task, and programming logic is the logic we use basically to solve that problem. So basically it's a set of principles that solve a problem. That is programming logic. For example, in a very simple way, I'll tell you. So if you're going to a shop to buy something, that is your problem. So the logic would be, what is the best way? You will be thinking, what is the best way to go to that particular shop, whether by walk or you have to take a cycle or a bike or a car, motorbike or a car. So all those things, right? And then you need a route map, you need a budget, a lot of things that comes through. So you think through everything before going to that particular shop, and then you execute that. That is how you solve a particular problem. right? So your brain inherently does a lot of things you don't even notice. So like, think about it. You have to carry a purse. If you go to a shop, you have to carry a purse. You have to check for fuel in your vehicle. You have to take the keys. You have to take your credit card or cash, whatever it is, right? So everything you will subconsciously you will do if you want to go to a shop. So all these things the brain will take care of itself. So, but that is basically our logic, right? So our brain ensures that everything works according to the logic, and similarly we have our programs are also going to do the same. So it basically, so from the example we must have understood that it is basically organizing of elements involved in the process, and then we modularize. Sometimes what we do, sometimes if it is a complex process, we modularize it. Okay, first say for example, if we want to go to a longer distance, we probably split it into three modes of travel. So first we go to a specific location by a train, and then take a bus, and then we hire a taxi or something. So basically we modularize and execute one process by process. So that is modularization, dividing a larger task into smaller chunks, and then we make some logical choices. We may reuse. In terms of programming, what we will do is we will reuse a specific logic. So say for example, you're going to take an auto, right? You're going to take a taxi or an auto rickshaw. So in that case, in certain cities you need to negotiate with the drivers for the fare. Okay, so that is a process. Now you will reuse the same process in other locations also. You try to negotiate so that you get a better bargain. So that is reusability or repetition of logic. And then progression is like, okay, we extrapolate, and then we think, and then we use it. Say for example, okay, for this step I did 1,000 steps, so this is a double distance, it should be 2,000 steps, and you calculate the time. So like that you progressively think and make decisions, and then you make conditional decisions. So if this is the condition, do process A. If this is not the condition, then do process B. So these kind of decision making, conditional decisions. And then best practices adaptation, that is also another logic. So best practice adaptation is very simple. Somebody might have used some logic and they tell you that is the best, that is the best way of doing things, and then you simply adapt it without thinking anything of your own, right? So that is the best practices. So these are all several ways of the thought process that is involved in a programming logic. Now how do I was talking about all this real life examples, like going from one place to another, right? So start from a source and then arrive at a destination, a shop. So we do a lot of organizing elements, modularization, choice, everything we do from our brain, right? So how do we learn, how do we evolve doing all these things? That is a big question mark. From where did it start? How did it evolve? All these are the interesting questions that we have, right? So in earlier days, humans are like, when humans were, let's say, amoeba, They are destined for only one process, which is to eat and then eat and then eat. That's it. Right? Then we evolved into something else where we we were like we were like animals, where we understood we were hunter gatherers. We understood that if we go to a specific location, we might find food. So from the stage where we find we eat if we find something, to we go to a specific location to find food. So that is one evolution. And then every day we go there. That is another evolution, which means we had developed a routine. We modularized it and then we had developed a routine. Then after some time, when I say some time, it is thousands of years, hundreds of thousands of years basically. We started creating our own food. And then after some time, we started creating food and then storing it. So all these things happen based on the food for us. Right? So similarly, we started thinking for food, we started thinking for food, we started thinking for our survival, and that is how the logic and everything evolved. So similarly, if you take computers, earlier it used to be single purpose computers. What do I mean by single purpose computers? A computer that can do only one job. Say for example, your a microcomputer that is inside a device, or something like say for example inside your washing machine. So that computer cannot do any other job. It can do washing. That's it. So that's a single purpose computer. It doesn't have much memory. When you switch on, you can program a couple of things, like whether you want a hot wash or a cold wash, and you can configure the cycle time and everything. That's all, and it will repeat the same thing again and again. That is the use of a single purpose computer. We have a lot of examples for that. Earlier days we used some very small microprocessor like 8086, 8085 and all that, and then use it for like creating some such kind of devices, controller for devices, and then we use it for creating, like, for communication devices like EPABX systems. In earlier days we used to have private branch exchanges for telephones and all, right? If you are an enterprise and your company has multiple extensions, then you manage your own private exchanges. So those things are controlled by such microcomputers. So these are all single purpose computers basically. And then came the multi-purpose computers and modular programs. So what is multi-purpose computers? What they did is, there was a guy named von Neumann. He defined an architecture called von Neumann architecture, where he advised to keep the memory out of the computer so that the memory can be accessed by external devices outside of the chip, microcomputer, the CPU, right? So that anybody can put anything in the memory, all that. So, and then so that is the revolutionary thought. So that came into use, and then the memory came out of the computer. So we started managing the memory from outside of the computer, like using an operating system kind of thing. And then that helped computers do multiple processes at the same time. So how does it happen? So how the computer chips, how they work is, when you give an instruction, it processes it, right? So what we do, we keep on giving instructions one by one. Like for, we keep on giving instructions one by one, and then we also give a pulse to execute it, saying that okay. So this pulse is called a clock pulse. So every time this clock pulse hit the CPU, then this instruction gets executed. So that is, so we in a processor we see the configuration like 2.5 gigahertz, 2.8 gigahertz. This hertz is the measure of the frequency of the pulse that happens in a second in a computer. So so basically it defines the speed of the processor. So basically if it is 2.4 or 2.8 gigahertz, then the pulse may be like in 1 second it can process 2.8 giga instructions. So that is how basically the processor speed is defined, and based on this clock pulse every instruction is executed. So now since we moved the memory externally out of the processor, out of the CPU, now we can define specific spaces for each program, and then on each pulse we execute one instruction from, let's say we define 3 processes. Okay, so for each pulse, first we do the instructions for the first processor, then on the second pulse we do the first instruction of the second process, and on the third pulse we do the first instruction of third process, and then go back into cycle. Like for the fourth pulse we do the second instruction of the first processor, like that. So now since this is very fast, it will look like all the 3 programs are running, but eventually it is time sharing. The processor gets time shared between these 3 processes. So these 3 processes, this is how the multi-purpose computers, and all multiple programs started running on computers, and also the modular programs. So high level languages, they started defining modules, and high level languages, they start defining modules, and then these modules get structured in a way that they can be reused, they can be realigned, and the entire programming is very efficient in several ways. So all these made the computer more smarter, and it evolved like how humans evolved from being an amoeba to animals. Like now, then came the object-oriented programs. So what is an object-oriented program? So compare this. A human, after he started growing his own food, he started saving it for the future, right? So everything he saved became very precious to him. He started saving food, he started saving his the protection gear, the weapons, started saving his dress, clothings, everything, and then these all became very, very essential for them. So the thinking process totally changed in him, and he started finding usefulness in everything he sees, and then he started saving them. So that is how we started to think everything in an object oriented way. Today what we do is we see everything as objects. You see your mentor, your friend, everything as an object, and everything has a purpose or a use in your life. There is nothing that is not useful for you. So you think everything as an object. Can you tell me one thing that is not an object? You cannot, because everything is an object. Say for example, else it will be a garbage for you. That's all. So you take, say for example, you have a pen. Until it writes, it is an object, it is a pen, you use it. Then you throw it away, it is a garbage. That's all. Whatever you throw it in the garbage, that becomes garbage. Right? Even humans in that sense, philosophically. Right? You have a name, you have everything, you have functions to perform. Then after your death, basically you are a body, dead body. Right? So that is how our mind is thinking these days. And we also made our computer think in the same way. So that is where object oriented programs evolved. And today's programs are mostly object oriented, and it was designed in such a way that so that it will be easy for us to command and control. It will be easy for us to say, hey, take that object, put it here, take this object, throw it away, like that. So it will be easy for us to control. So that is where the object oriented programs come into place. So we are going to discuss about object oriented programs in detail in our next session. So don't worry about that. We are going to totally disintegrate, analyze, and completely get a classic idea about what object oriented programming is all about, because modern languages, they basically work on object oriented nature. All right. So that is for today's session. So from today's session, what we understood is we need programming logic for writing software programs effectively. So programming logic are nothing but arranging and organizing the elements of a program effectively, like modularizing, reusing, etc., etc. And then understanding the similarity between how the human evolution and the program, the software evolution. That is what we did in this session. Hope you enjoyed this session. Let's meet in another session tomorrow. Thank you for your attention. Have a good day. Bye and good luck.